Okay, now we're ready to write a proof of the mean value theorem. It's not very hard, but let's start by saying that f is a function on the closed interval and that it satisfies the three properties. So f is continuous on the closed interval, or the two properties rather, I'm sorry. And number two, that f is differentiable on the open interval AB. We want to prove that there is a number c where f prime equals the slope of the secant. So a diagram can help guide us to what we're going to do. So similar to before, let's build a function. Here's a, here's b, here's f of b, here's f of a, and in blue here I will sketch my graph. And now I will draw the secant line. Okay, and if I look very carefully here, maybe I can locate the point on the graph that has a tangent line that is parallel to the secant line. I think that's where it is. Actually, there might be another one. If I'm really careful, I think I could do this here. There we go. So here there's actually two values, 2 points C, right here and right here, where f prime equals the slope of the secant. Slope of the tangent equals slope of the secant. But what I'd like you to do is think about how would I write the equation of this green line. How would I write the equation of this green line? Let's call the green line L. Let's say L is the secant line. And it goes through the points A, f of A, and B, f of B. So it goes through those 2 points. Well, first of all, we need the slope. The slope of this line is, of course, f of B minus f of A over B minus A. So that's the slope. And then the point slope formula gives us y minus y1 equals the slope times x minus x1. So we're calling this function L, so let's just say, and by the way, y can be written as m times x minus x1 plus y1. So our function is called L, so let me just say L of x equals the slope, which is f of b minus f of a over b minus a. And maybe we'll use this point here in my equation. So that's my x1, y1. So x minus x1 is a, plus y1 is f of a. So here we go. This is the equation of this line L. Okay? And this blue graph is, of course, f. Now we're going to build another function called g. And here's what I want g to be. G of x is equal to my original function minus this linear function. And the idea is the mean value theorem has these two conditions, 1 and 2. We're going to build another function called g that has 1. G is continuous on the closed interval AB. Why? Because f is continuous and linear functions are continuous, and when you take the difference of continuous functions, then the difference is continuous. Number two, g is differentiable on the open interval AB. Again, f is differentiable, linear functions are differentiable, and when you subtract differentiable functions, the new function is also differentiable. But it has a third property. It has a third property. If you plug in g of a, if you plug in a in the g, then I get f of a minus L of a. And as you could see from the graph, they're the same y value. Or you can just plug in L of a into this equation. What happens is you get the slope times a minus a plus f of a. This is 0. So L of a equals f of a. So the difference is 0. And if you plug in g of b, that's basically f of b minus L of b. And again, coming up here to the graph, right here and right here, they have the same y value. Again, f and L meet. And if you plug it into the graph, or to the equation, L of b would be, here's the slope, x minus, we're plugging in b, right? I'm sorry. We're plugging in, this is x minus a plus f of a. Instead of x, we're plugging in b. So that would cancel. So then we'd have f of a minus f of a plus f of a, in which case these two cancel. So the answer would just be f of b. So f of b and L of b have the same value. For this reason, this is 0. But more importantly, what we've established is that these two are equal. So g of a equals g of b. So now g satisfies the three requirements of Rolle's theorem. So now we could use Rolle's theorem. What does Rolle's theorem guarantee? That g prime of c is equal to 0 for at least 1c in the interval AB. So let's take a look at this function g, and let's take the derivative of that. Oops. Let's take the derivative of this. Okay? The derivative of that function is g prime of x is equal to f prime of x minus L prime of x. So g prime of x is equal to f prime of x minus, now L is a linear function, so its slope, or its derivative, is the same as its slope. It's constant, doesn't depend on x, it's just a constant number. And then so the c guaranteed by the Rolle's theorem for g. So g satisfies the three properties of Rolle's theorem. So c guaranteed basically is saying that g prime of c is 0. So in other words, that 0 equals f prime of c, plugging in c instead of x, minus f of b minus f of a over b minus a. If I rearrange this, then I get f prime of c equals f of b minus f of a over b minus a, which is exactly what the mean value theorem was saying about the function f. Okay, I agree it's too much to take in for the proof of a single theorem, but it's important that you see this one time and read it over again, watch the video again, read the book, try to make sense of it for yourself. But the overall idea, again, the strategy that you should keep in mind is that we're trying to prove a theorem about f, and f has these two conditions, and Rolle's theorem comes first. So we could use Rolle's theorem, but we need to build a function that satisfies the third property, and f doesn't. So you write the equation of this secant line, and then you notice that if you build a function g that comes from the difference of your original function and the secant function, then that function will satisfy all three properties, and then Rolle's theorem works. Okay, and it turns out that Rolle's theorem makes the function prime, the derivative, equal to 0, but that just makes the original function have a derivative equal to the slope of the secant at some particular number c. So that all comes together in that way.